Uh, let's take a look at some practice problems with gas mixtures. So number one, a mixture of helium and argon. And so in this we have helium and argon. Occupies a volume of 1 times 10 squared liters. So 1 times 10 is 100 liters. So we got a 100 liter helium argon mixture. The partial pressure of helium is 0.6 atmospheres. And so here, the helium pressure is 0.6 atmospheres. The argon pressure is 0.4 atmospheres. And so what this means is that if you look at this, this means that 60% of the collisions are helium, 40% of the collisions are argon. Can you see that based on the ratio here? Okay. And so that means this. That means that this is equal to 100 liters of helium. With a pressure of 0.6 atmospheres. Plus 100 liters of argon at a pressure of 0.4 atmosphere. And what is the total pressure of the gas in here? Well, if I have both gases in there, then the helium is going to exert a pressure and the argon is going to exert a pressure. And so for every 100 molecules, 60 of them are helium, 40 of them are argon. So if I separate out the helium from the argon, or the argon from the helium, this is what results. And so 100 liters of mixture is equal to 100 liters of helium, which is equal to 100 liters of argon. And so what I'm going to do is I'm going to take 100 liters of helium and add to it 100 liters of argon. So if I take 100 liters of helium plus 100 liters of argon, how many liters of mixture do I get? Yeah, normally if you take 100 liters plus 100 liters, you should get 200 liters. But what we're going to do is we're going to just compress it into one box. Well, what's going to happen? Well, it's going to go higher in pressure. And so this is going to be 100 liters at, okay, now if I take 0.6 atmospheres plus 0.4 atmospheres, that's going to give me 1.0 atmospheres. And so I have 100 liter mixture at 1.0 atmospheres. And this is the way we visualize it using Daltons or Avogadros. This is the way we visualize it using Daltons. That is the pressure, the total pressure is equal to the pressure of the helium plus the pressure of the argon. This is Daltons. And this is how I've drawn it up here. But we also have the choice of Avogadros. If we use Avogadros, then I don't say the pressure. Instead, if I use Avogadros, I'd say that the total volume is equal to the volume of the helium plus the volume of the argon. This is Avogadros. And so what I did was I visualized this mixture as a Daltons. That is, 60% of the collisions are going to come from the black molecules, 40% of the collisions are going to come from the green. And so that means 60% of the pressure will be the black, 40% of the pressure will be the green in this box. Now, for Avogadros, I'm going to visualize it differently. This is the way I do it for Avogadros. For Avogadros, I'm going to split it into different boxes. So but the boxes aren't going to be the same. What I need to do is I need to maintain the pressure. So I have 100 liters of mixture at a total pressure of 1.0 atmospheres. So it's the exact same thing, 100 liters of mixture at total pressure. But now what I'm going to do is I'm going to split it up into two boxes. I'm going to have a box for helium. Now how big of a box do I need for helium? Yeah, I'm going to need a 60-liter box for helium. So I'm going to get 60 liters of helium. And what that's going to do is I'm going to keep the box the right size. The right size to maintain what? The right size to maintain the pressure. So it's going to be 1.0 atmospheres of helium. And so I get 60 liters of helium and maintain that pressure of 1.0 atmospheres. And so the pressure is the same. Plus, how big of a box do I need for the argon? 40. I need 40 liters for the argon. So I'm going to have 40 liters of argon. And what's the pressure of the argon? Well, I got to make sure. I'm going to cut down the size of the box to make sure that the pressure is maintained. So it's going to be a smaller box. And so I'm going to end up with 1.0 atmospheres argon. So however many collisions I have here, I'm going to have the same number of collisions here and the same number of collisions here. That is, the pressures are all going to be the same. If the pressures are all the same, then what's different is the volumes. And so I get 60 liters plus 40 liters gives me 100 liters of mixture. And so what we can say is that V total is equal to the volume of the helium plus the volume of the argon, as long as we're dealing with constant pressure. This is the key. It's constant pressure. Dalton's is constant volume. And so Avogadro's is constant pressure, Dalton's is constant volume. And so there's two different ways of visualizing it. And so here they're doing the two ways of visualizing it in problem number one. In problem number one, the first way of visualizing this mixture is via Dalton's. That's 0.6 atmospheres of helium plus 0.4 atmospheres of argon is going to give me 1 atmosphere of mixture. Now they're asking, what are the partial volumes of the gases? Well, the partial volumes is if I have 100 liters of gas, then it's got to be 60 liters of helium and 40 liters of argon. And so those would be the partial volumes. So the volume of the helium is 60 liters. What? I guess I never read this answer. This answer doesn't make sense. Use gas filled with the volume of the container. The gas, either pure or a mixture, is made of tiny particles that are widely separated so they can occupy the full volume. All right, this is what they're saying. What they're saying is that, okay, if I have 0.6 atmospheres of helium, how many liters of helium do I have? Well, to get this lower pressure, I have to have a bigger box, so it's going to be 100 liters. And so the answer, what they're doing is they're just saying this. They're saying that the volumes are all the same. That is, if I have 100 liters of mixture, 100 liters of mixture consists of 100 liters of helium and 100 liters of argon. So 100 liters plus 100 liters gives me 100 liters. So the volume's always the same. And so what's going to differ is the pressure. In this 100 liters here, I'm going to have, just looking at the black, I'm going to have 0.6 atmospheres worth of collisions. And just looking at the green, I'm going to have 0.4 atmospheres worth of collisions. But they occupy the same box. And so if I look at this box, this is a 100-liter box. In this 100-liter box, how many liters of helium do I have? This is why you need to orient yourself. You got to orient yourself. Are you visualizing this mixture as a Dalton's mixture, or are you visualizing it as a Avogadro's? Because I only have this box. I have a 100-liter box. It's at 1 atmosphere. It's filled with helium and argon. 60% of it is helium. 40% is argon. That's always true. And so this is going to be 60% helium, 40% argon by mole, so the number of molecules. Now, if somebody asks you how much helium is inside this box, you have two answers. How much helium is inside this box? 100 liters. 100 liters of helium inside this box, 100-liter box. It is 100 liters because helium is occupying 100 liters. That helium can go anywhere it wants in this 100-liter volume, correct? But if you say 100 liters of helium, then you can't say it's at 1 atmosphere. You have to say it's at 0.6 atmospheres. And somebody asks you, well, how much argon do you have? Well, you say, well, I have 100 liters of argon, because the argon can go anywhere in that 100-liter box. But you can't say it's at 1 atmosphere. You have to say it's at 0.4 atmospheres. Okay, that's answer number one. Answer number two is, I have 100 liters of mixture. How much helium do I have? Well, I got 60 liters of helium. Well, if you have 60 liters of helium, then it cannot be at 0.6 atmospheres. It's got to be at, because you're compressing the box, it's going to be at 1 atmosphere. And so you can say I have 60 liters of helium at 1 atmosphere, or I have 100 liters of helium at 0.6 atmospheres. How much argon is there? Well, this is going to be 40 liters of argon at 1 atmosphere, or I could say I have 100 liters of argon at 0.4 atmospheres. Does that make sense? And so there are two answers for this. The two answers are depends. Are you looking at this as an Avogadro's over here, or are you looking at it as a Dalton's over here? Two, a mixture of argon and carbon dioxide gas is maintained in an 8.05 liter flask. So I have, now I got 8.05 liters of mixture. And it's going to consist of argon and CO2. So argon and CO2. I don't know if it's a 50-50 mixture or what it is. How much argon, how much CO2. If the partial pressure of the argon is 0.326 atmospheres, so they're telling us the pressure of the argon is 0.326 atmospheres. And the pressure of the CO2 is 0.234 atmospheres. Then what is the total pressure of the flask? And so then this is a little simpler because they're doing this as what? Daltons or Avogadro's? Daltons. Avogadro's would have the two pressures the same. So now I got argon colliding with the wall. The argon's colliding with the wall is generating 0.326 atmospheres. And then I have CO2s colliding with the wall. The CO2s colliding with the wall is generating 0.234 atmospheres. Now what is the total collisions generating? The total collisions, that is the argon and the CO2 collisions in total, well, it's just going to be the collisions generated by the argons plus the collisions generated by the CO2. That's going to be the total pressure of the mixture. And so that's 0.326 plus 0.234, which is going to be, what is that going to be? 0.560 atmospheres of total collisions hitting the wall. Do you see that? This is what we call Daltons. This argon, how much argon do I have? I have 8.05 liters. How much CO2 do I have? I have 8.05 liters. Because it occupies the whole box. Versus Avogadro's. Avogadro's would look at this mixture differently. Avogadro's would split it into smaller boxes. So for example, I know the total pressure is 0.560 atmospheres, and I want to maintain that pressure. So I want the argon to maintain the pressure of 0.560 atmospheres. That means I have to cut down the size of the box to get the same number of collisions as the total. And so this is going to be a smaller box. I have to get the percentages though. And so the percent argon is going to equal 0.326 divided by 0.560 times 100%. So what does that come out to? .326 divided by 0.56. 58.2. So 58.21% of the pressure of the atmospheres is argon. And the percent CO2 is going to equal 0.234 out of the total 0.560 times 100%. So this is 0.234 divided by 0.56, 41.78% CO2 by pressure. And so what I need to do is, if I'm going to split this up into argon, it's 58.21% of the volume here. And so what is 58.21%? Well, 58.21% of 805, so it's going to be 58.21 divided by 100 times 8.05. So 58.21% of this volume is 4.685 liters. 4.69 liters of argon plus, okay, the rest, minus 8.05, which is the total, is going to be 3.364 liters of CO2. And so 4.69 plus 3.64 is going to give me 8.05 liters total. The only thing is when I cut it down into smaller boxes, I can maintain the pressure. And so what I'm going to end up with is I'm going to end up with 0.560 atmospheres of argon and 0.560 atmospheres of CO2 and 0.560 atmospheres of mixture, because I'm going to put these two boxes side by side, let them mix. Does that make sense? Okay. 3. Atmospheric pressure is the total pressure of the gaseous mixture called air. Atmospheric pressure is 749 on a day. Okay, so I'm going to have an air mixture. So this is air. And the total pressure is 749 torr of air. That the partial pressures of nitrogen, oxygen, and argon are respectively. What are the pressures of the other gases in the air on that day? So again, we're going to be thinking in terms of Daltons. That is, P total is equal to the sum of the partial pressures. And so P total is equal to the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the argon plus the pressure of the other gases. And so this is what we're going to find out is it's going to be 584 torr for the nitrogen plus 144 torr for the oxygen plus 19 torr for the argon plus X torr for the other gases. And then we just solve for X. So we'll just take the total, 749 minus the nitrogen, 584, minus the oxygen, 144, minus the argon, 19, and that leaves us with 2 torr left over. X is 2 torr. And so what is the other gases? The other gases are going to generate 2 torr. What are the other gases? Helium, whatever else. We have, let's just check the answer. So it's 2 torr. Okay, the stopcock connecting a 1.00 liter bulb containing oxygen gas at a pressure of 540 torr. Okay. So what this is we have O2 gas at 540 torr. And the volume is 1.00 liters. Okay, this is going to be connected, there's a valve here, and this is going to be connected to another 1.00 liter box that is helium gas at a pressure of 776 torr. So this is going to be helium gas at 776 torr, and it's going to be 1.00 liters. The gases are allowed to mix. What is the final pressure in the system? So we're going to open the valve here. We're going to let the gases mix. So if we open the valve and let the gases mix, what will be the final pressure? This is, in a way, this is a gas mixture problem. In another way, it's a combination problem. What happens if I have a gas, oxygen, and I double its volume? That is, I have 1 liter of oxygen, and now I'm going to double its volume, make it 2 liters. What's going to happen to the pressure? It's going to be cut in half. And the same thing with helium. If I go from 1 liter to 2 liters, that's going to be cut in half. And so this is kind of a mixture and one of the earlier laws problems. So if I open this, the total volume gets cut by half. And so what I'm going to do is I'm going to have to calculate the new pressure of oxygen. And so once I open the valve, I get the new pressure of oxygen. The pressure of oxygen is equal to V initial over V final times the pressure of oxygen initial. And so this is the final pressure of the oxygen. And so the initial volume of the oxygen is 1.00 liters. The final volume of oxygen is going to be 2.00 liters. The initial pressure was 540 torr.